Hello, everyone. Glad to be here at AI Dev 2025. And today I'd like to talk to you about vector search, vector databases, and the OpenSearch project. But just to get to know you folks, with a show of hands, who today uses OpenSearch one way, shape, or form? OK, I see a few hands. Come to me afterwards. I'll give you a shirt like that, and curious to hear how you use the project. I'm Dotan Horovits. The picture you see here, by the way, is from Amsterdam, just a few months ago, back in April, when we held the OpenSearch Con Europe, our yearly regional event. I'm an evangelist for the OpenSearch project. I'm a senior developer advocate at the AWS open source team. Outside of AWS and my day job, I'm also a CNCF ambassador. I also run the Open Observability Talks podcast. And as you can see, you can find me everywhere at Horovits. My surname is my handle. So if you're posting anything from this talk, feel free to tag me. And also, if you want to reach out after the conference, happy to reach out. So let's start with lexical search. We've been doing it for a long time, essentially searching for keywords. That's been working well for us. It's fast, it's accurate. You can see the example query here, essentially if I'm looking for the book The Martian, that's exactly what I want to find, that book with that title from my catalog. So you can see the match query on the screen with the relevant keywords on that title field. And lexical search would work just as well also for finding all books that have Martians in them, whether in the title or description or something else. But lexical search lacks the meaning and intent of our query. For example, what if I want to find books that involve any sort of alien, Martians or otherwise? This is what semantic search comes to solve. Let's try searching for sailboat shoes. You can see here, side by side, the two OpenSearch queries. On the left, you see the match clause for lexical search, and the other, the neural clause for neural search, for semantic search, using a given LLM. So both searching for sailboat shoes. Let's see how they did. So as you can see on the left-hand side, the lexical search returns results. Let's see, sailboat decoration I see here, sailboat pendants, girls' sailboat dress, sailboat earrings. Not exactly what we intended. On the right-hand side, you can see that the semantic search returns results that are much more relevant to our intent and meaning, sailboat shoes. So search is evolving from lexical search based on keywords into semantic search based on meaning and intent. And I want to dive into what semantic search is and into dense vector search. So in semantic search, we encode the data as vector embeddings and run searches on the embedding representation of our data. A vector embedding is a vector in a high-dimensional space, capturing the deeper patterns and similarities in meaning, context, and structure in our data. So you give it some text, for example, and the resulting embedding is a series of floating point numbers, so one per dimension. So if you have 300 dimensions, you'll have 300 such floating point numbers. And by the way, today's models go into thousands and tens of thousands, so it's not rare at all. The embeddings themselves are generated with ML models, with LLMs, or small models. They essentially use deep neural networks to understand the meaning and context of our queries and create that dense vector for us. The semantic similarity is essentially manifested then in the various dimensions of our embeddings. I tried illustrating it. So if you have cities or animals or vehicles, you'll see in certain dimensions that the numbers are in very close range, in close proximity. So that's the gist of it, and I'm no mathematician, but that's the principle. And of course, it does not have to be just text. Embeddings can be generated for different modalities, such as audio, video, images, PDF documents, which themselves, PDFs usually have different modalities. So think about the embedded graph and the chart and the table in that PDF, and their headers and paragraphs. So PDFs are multimodal themselves. And actually, there's a talk here tomorrow about searching unstructured PDF documents by Mingxi and Praveen. So check it out tomorrow at 11 in the morning. So different embedding models specialize in generating embeddings for different modalities or even multimodal models. So in lexical search, we use algorithms such as BM25 to calculate the relevance, the similarity of our document to our search query, okay, based on term frequency and occurrence models. With embeddings, the similarity is calculated by the proximity in that multi-dimensional space. Essentially, we take the embedding of our query and find the embeddings that are closest to it in that space. So let's dive deeper into what that vector proximity means. So first, we need to determine how to calculate the distance between two embeddings. This is called the space. And the different spaces, you can see some examples here, like Euclidean, cosine, inner product, Hamming, and others. And again, I'm no mathematician to explain to you these complex formulas, but just remember that each distance calculation method has its advantages based on your use case. Some better for recommendation systems, some for document classifications, for collaborative filtering, and so on and so forth. After we determine the space, we can run the algorithm for finding the k nearest neighbors, the KNN algorithm. Now, the exact KNN algorithm is essentially a brute force algorithm. It runs exhaustive comparison to every vector in our multidimensional space. So, of course, it guarantees the most accurate result, but on the other hand, it scales poorly to large data sets and to high cardinality for many dimensions. So it makes it impractical for many use cases. And in these use cases, we use approximate KNN, sometimes called ANN, which trades some accuracy for much faster search times. And it scales better, of course. So there are several algorithms. There's HNSW, the hierarchical navigable small world. There's the IVF, the inverted file. Again, not going into the algorithmic side of it, but different algorithms and also different engines implementing it, such as Lucene by Apache or Feist by Facebook or NMSlib or others. Running this semantic search based on embeddings, using these methods, spaces, algorithms, engines, LLMs, all of that on high cardinality, that's what vector databases are come to solve. So I'd like to introduce the OpenSearch vector database. It's an open source platform for AI-powered search and analytics. It was initiated by AWS. And during last year's Open Source Summit Europe in Vienna 2024, the OpenSearch project has become part of the Linux Foundation. Actually, we just celebrated the 1-year anniversary a couple of days ago here at the Open Source Summit Europe 2025. So I want a big round of applause for everyone who made that happen. That was a big, big, big milestone. Way to go for everyone who contributed to that. And really, we can see organizations such as Uber, SAP, NetApp, and more that have joined already and are helping drive this project forward. So that's a bit about the project and the community. And OpenSearch, let's talk about what OpenSearch is for. So essentially, it's a search engine with many use cases, as you can see, for lexical search, for observability, log analytics, for security analytics. But for this talk, I'd like to focus about using OpenSearch as a backend for the AI and ML-powered application. So let's zoom into that. Based on all the background that I gave you at the beginning of the talk, OpenSearch essentially offers a full-fledged vector database for storing your dense vector embeddings and running similarity search on them. It can scale trillions of vectors. There was actually a great talk this morning about how it reaches that scale. So I don't know if you saw that. If not, check out the recording. OpenSearch supports both exact and approximate KNN algorithms using multiple engines, supports different modalities and even multimodal search. In addition to the dense vector search, it also supports neural sparse search. You can bring your own LLMs. So lots of goodies, and I want to see how it's done. So you can use OpenSearch as a simple vector database to store your raw vectors, as you can see here in this query example. This means that you can write vectors into OpenSearch and then provide the vector of your query, and OpenSearch can then run the algorithms to find the nearest vectors and returns them. That, however, means that it's up to you to transform your data into vectors for ingestion, and then transform the queries into vectors as well, so you can run the similarity search, and then when you get the resulting embeddings, you need to then transform them back to get the original data, and then what if your text is too big for the model, or your data has multiple modalities that require different models? Most users don't know how to do that, and they don't want to deal with all of that. Most users don't want to see this, they want to see that. They want to put their data in simple text, PDF, images, whatnot, and then query the data, typically in text, and not deal with all the vectors. They want essentially the semantic search experience. And OpenSearch allows you to do just that. It takes care of all the transformations from data to embeddings and back to the resulting data under the hood and all the other tasks for you. And I want to see and to show you how it's done. So you send your data with different modalities, as we mentioned, text, audio, video, PDF documents to OpenSearch core. Then it undergoes text chunking, which involves splitting long documents or text passages into smaller segments to improve the search, retrieval, and relevance. Because most embedding models have token length limitations. So chunking helps maintain the quality and relevance of the vector search results by ensuring that each embedding represents a focused piece of content that fits within the model constraints. So OpenSearch offers this text chunking processor that you can then plug in as a pre-processing step. Then ML transformer models are used to generate the embeddings, as we said before, for different modalities, and then the embeddings are indexed, stored, and are made available for all sorts of ML-driven search applications. And when you need to query that data, you just write your query text. Of course, you can also have an image or something else, and then a similar process will convert that query into embedding using the same model, and then run the KNN algorithm to find the similar embeddings with their respective relevance scoring, and then return the respective documents for each and every one of these embeddings back as a result with a respective ranking. And note, I put it side by side so it'd be very clear. You're querying the data as text and getting the resulting documents. You don't need to directly interact with the embeddings in the process. OpenSearch provides many pre-trained models. For example, there are at least a dozen text embedding models that you can find open source on Hugging Face, open for you to use for any purpose. And you can also upload and serve your own custom model, of course, for locally in OpenSearch for your specialized use cases. But what if you want to use one of the popular LLMs services out there? Okay? The great thing is that we have such a plethora of models coming in every day, and we want to leverage them. And OpenSearch provides an easy integration to all these models through ML Commons, which is an ML-based library with blueprints that allow you to easily connect or develop new connectors to all these LLMs. So you already have out of the box, you can see some examples here, Cohere, OpenAI, and DeepSeek. And it's so easy, by the way, that when DeepSeek came out, it only took 2 days to have the connector up as part of the open source project. So it's very friendly and very easy to integrate new models. Vector search workloads are heavy on memory. We also heard that today on the keynote, whoever was here. And I want to look quickly at a typical example for embeddings for a 100 megabyte document with OpenAI. So OpenAI's text embedding 3 small yields, what's that, 1,536 dimensions, each stored, as I mentioned before, as a 32-bit floating point. So that's 4 bytes for each dimension. That's about 6 kilobytes per vector. And when you chunk a 100 megabyte document into about 100,000 segments based on the tokens limit, you get essentially to 600 megabyte embedding data, which is 6 times the size of your original document. And that's actually conservative. In the keynote this morning, the speaker mentioned 25 times more, so it's definitely significant. And in order to reduce your overall cost for vector workloads, OpenSearch supports different types of vector quantizations. Think about these techniques as mechanisms to compress your embeddings. So essentially, you trade off some accuracy in return to reducing the memory requirements, at least by 2 times, but you'll see soon it could be much, much more so. So there are different quantization techniques to choose from based on your data and trade-offs. For example, with scalar and binary quantization, you can reduce the dimension size for each dimension from 4 bytes to 2-byte floating point, or maybe 1-byte integer, or maybe even 1-bit binary Boolean. This is one example. And with product quantization, you can actually reduce the number of dimensions themselves to reduce the overall cardinality. So again, not going into the math behind it, but you can find various ways to do that. Semantic search excels at understanding the intent and natural language, if you will, but may miss important keywords, especially with fact-based searches. And that is where hybrid search comes into the picture. Hybrid search combines lexical search with semantic search, so essentially keyword-based and vector-based, to improve the search relevance. And this approach ensures that the results include both exact keyword matches and conceptually similar content. A hybrid query, as you can see here on the screen, is essentially comprised of 2 subqueries of the types we already know. So you see here the match clause for lexical search and the neural clause for neural search. And I'd like to show you how it's being executed. So each subquery from those runs its own regular path to find relevant results using their respective algorithms and engines. So BM25 for lexical, cosine for vector, for example, and each one has its own different scoring mechanisms and ranges. And for that, we need to then run rank normalization to make sure that the scores produced by the different methods and search algorithms are brought to a common scale. Then we combine the results of the different subqueries, and then we can also give weights to the different subqueries. We can, for example, give more weight to the results for the keyword search for the BM25 over the results of the neural search. And when we get the combined score, then we fetch the original documents. OpenSearch does that for you, of course, and returns the resulting set. And there are different normalization methods and techniques. Essentially, they're divided largely into two groups, the score-based normalization and the rank-based normalization. Score-based is more, it works on the raw score, and rank-based works on the, focuses on the order, the relative order of the results in the set. And OpenSearch, as you can see, supports multiple such techniques. Again, not going into the math, but each technique has its own advantages based on your use case and based on the individual scoring algorithms that you need to combine. And there's more. I won't be able to cover all of that in a short talk, but just want to give you a brief taste of what it takes. Several popular LLM frameworks integrate with OpenSearch as a vector store or as a semantic cache to build knowledge-powered conversational applications, AI agents, RAG applications. You can see some of the examples here, LangChain, LlamaIndex, and others. Also, OpenSearch 3.0 introduced native MCP support, Model Context Protocol, to standardize the integration with AI agents. So if this is something that is relevant for you, and I saw many hands being risen in the air at the keynote when asked about MCP, it could be very relevant for you. And in general, OpenSearch v3 has many more goodies. I just recently had an episode about the 3.0 major release. I hosted the governing board chair, Carl Meadows, and the 3.0 release lead and technical steering committee member, Pallavi. So check out the QR code for the full episode with the authoritative source on the major release. And just to summarize what we've seen, essentially ML flows, machine learning flows, need a vector database to store the embeddings. And we talked about lots of terms here. We talked about embeddings, spaces, KNN algorithms, modalities, chunking, and so on. But what we want, essentially, is the semantic search experience. And OpenSearch provides this end-to-end semantic search experience for us. We can plug in our own models, as we saw. Lots of popular frameworks that we work with already have the integration. And very importantly, especially here with AI Dev under the Linux Foundation, it's open source, it's community-driven, product-ready, and under the foundation. So join us on GitHub, forums, user groups. We even have a user group here in Amsterdam. We just had a meetup yesterday, but many other places around the world. I've put all the useful links in one place, also tech docs, playground, roadmap, and many more. So you can scan this one QR code. You'll get all of the links. And of course, come by the OpenSearch booth to see cool demos, to discuss some more, to get some cool swags, and to chat about it. Or feel free also after the conference to reach out to me at Horovits. Again, my surname is my handle everywhere. I'm Dotan Horovits, and thank you very much for listening.